My talk today will be about the consistency of the antenna products in the MGEX environment. I will do kind of two parts of the presentation. In the first part, I will go into the released IOV patterns by ESA. So I try to show what is the impact within the MGEX environment if I use the IOV patterns instead of the one which I'm using now. And in the second part, then I tried as there are chamber calibrator receivers available from the UREF network, which have the full frequency spectrum. So we also have the L5 for Galileo. I made some PPP tests to see what is the impact if we use actually the L1, L5 patterns instead as the L1, L2, as the L5 is not available. From the IOV pattern test for the MGEX is basically, as they have been released by the ESA in 2016, we have now the chamber calibrated PCO and PCVs for the 4 IOV satellites. 3 of them are currently fully active, and I have used these 3 to make the tests. The goal of these experiments were basically to show or to see what is the impact of the released patterns if we compare them to the current used values. And all the solutions is done based on our MGEX solution. We see here on the table below, I want to show what is actually the difference between these patterns. The main difference is in the PCOs. We see here on the top line, we see the current values which are used. We see especially here for the set offset we have 95 centimeters. And we see for the 3 IOV satellites that these values are slightly different than the currently used. If we build then the differences between these 2 patterns, we see that we have for the satellite E11 and E19, we have more or less a difference of 10 centimeters in the set offset. However, for the satellite E12, it seems to be fitting much better, where we have an agreement of more or less 3 centimeters between the 2 values. And of course, compared to the IGS, where we at the moment we don't have the PCV patterns, I also introduced the released PCV patterns which were released for these 3 IOV satellites. All the evaluation for these IOV patterns, basically, I did the orbit comparison between the PCO from the IGS and the combined patterns for the IOV satellites. Additionally, made a second test introducing station-wise inter-system translation biases, which I will go slightly in the next slide to explain what actually the station-wise inter-system translation biases are. And the whole solution is based on the MGEX, on our MGEX products, basically. Here is a small typo. It's not 120 stations. It's based on 140 stations. And I did analysis for 60 days between the DOI 6 and 120 in year 2017. Here on the lower plot, you see the station distribution, which I used for the day 60, where the red stars remarks the GPS Galileo receivers, and the black dots is basically GPS only. For this comparison, I've only used GPS and Galileo within the solutions. I didn't use GLONASS and other constellations. Now I want to go shortly in an introduction what these inter-system translation biases are. In order to understand, one can make a small assumption. We see here basically we have a GPS station or a GPS Galileo station. If I then produce a GPS only solution, I get a coordinate here, which is now the light gray coordinate system. If I do a Galileo only solution, I will get slightly a different offset, a slightly different coordinate. And what we are now setting up in our process is basically we introduce a vector which represents the difference between the GPS and the Galileo coordinate. In an optimal case, this offset would be 0, which means that the coordinates from both systems are completely consistent. Now I want to go directly into the results. Firstly, I want to show the results of the orbit comparisons between the IGS and the IOV patterns. We see here the first plot. This is the orbit comparison for the day 60 for the satellite E14. Here, as I mentioned, the satellite E14 is a FOC satellite, so we have used the same patterns in both solutions. We see they are both quite similar as to be expected, as I haven't changed not the values. If I then go further and I look first at the satellite E12, this is a satellite which has the best agreement with the currently used PCOs. The difference is 2.6 centimeters. We see that these two orbits are slightly different. And if we go further to the next satellite, E11, which is now 11 centimeters, we see that the orbits are already starting to be slightly different. And then for the last satellites with the largest offset difference, we see, of course, that we also have the largest differences. From this plot, however, I cannot say which orbit is better. I can just see they are different. But of course, I don't know which one is the truth. So to try a bit more to see what is actually the behavior of these different orbits, I produced the midnight epoch overlaps for the 60 days. So basically, I took the midnight epoch between 2 days, between 1 day orbits, and I compared what is the difference between at the day midnight boundary, so from the day 60 and of course then the morning of the day 61. We see here on this plot with quite a lot of dots. We see the gray dots. This is the differences based on the FOC satellites, and the color dots, the red, green, and blue, show the 3 satellites, E11, E12, and E19. This solution is now the solution where I use the IGS patterns. And then I get a similar plot. I can do the same analysis if I use actually the IOV pattern, the released one. And one can see there's not a huge difference. So within the next plot, to show actually what's the difference, I plotted the difference between these two solutions. Of course, again, as to be expected, the gray points are quite similar in both solutions, the patterns have not changed. For the other ones, which I have the patterns, I see that I have a difference between the overlaps. It has to be mentioned that if the IOV overlaps are smaller, I get a positive difference. So this means on the upper part, I have a better, with a more consistent orbits, and the lower part means that the overlaps are bigger. Basically, what I can see from this plot, I can't say that I see a clear improvement or degradation of the orbits. So with this plot, I can't really see directly if the impact would be better or not. The next test is then actually to look at these inter-system translation biases. So I produced a new experiment where I introduce again the IOV patterns and this inter-system translation bias and produce the orbits and this offset between the GPS and the Galileo satellites. I introduced 2 different sets of offsets. One offset is between the GPS coordinates and the coordinate based on the FOC satellites, which we see here. And the other one is then the comparison difference between the GPS and the actually IOV satellites. We see here, if I use the IGS values and the IOV, that for the FOC satellites, of course, I don't see a really difference. Here, yes. Here's a misspelling in the figure. This is actually the FOC using the IGS values. However, if I go now and look actually at the inter-system translation bias for the IOV satellites, we already see that, of course, the scattering is much higher per day. I forgot to say, we see here on the lower part, we see each station has a number, and all these inter-system translation biases for the 60 days are plotted in one row for each station, for east, north, and up. As this solution is just based on 3 satellites, we see that we have much higher scattering within these 60 days. If I now use the IOV satellites, we see actually that the scattering is getting a bit lower. So the consistency of this bias, I would say, seems to be more consistent. And I tried then to show this up by creating actually a table to get some numbers out of it, to make it more, to have a better view in numbers. We see on the top table, this is the difference between the IGS solution and the IOV solution, which has the IOV patterns. We see for the FOC satellites, basically, they are very similar as to be expected. However, the more interesting part is on the lower table, where I see the difference for the IOV satellites. What is especially interesting is on the right side, we see the mean scattering of a station. And we see that with the IOV patterns, actually, this scattering is getting much lower compared to the IGS value. So there, actually, I see an improvement that it's more I would say, more stable over time. We also see here that the actual value, like this is the mean value of this offset, it gets a slightly lower. However, it's still a quite high scattering. We see here the improvement is roughly between 30 and 40%. This was basically all I wanted to say about the first part. The second part is now I did some tests using the chamber calibrated receiver stations. Within the UREF network, at the moment I could find in the Antex file, I contained 12 stations which are actually chamber calibrated antennas, which have the L5 frequency within it. So the goal was now to see what is the impact of these L5 antenna patterns if I use them instead of the L2, which is usually done because the L5 is not available. And again, I set it up an inter-system translation biases, and I made two solutions, one for L1, L2 pattern using it, and the other one then using the L1, L5 patterns. For both cases, I used always the pattern from the chamber calibration for these 12 stations. We see here now the results. Now first it's an overview of the patterns. And we see here the stations which I could use. We see most of the stations, they have a Javad antenna, and the other part is from Leica antennas. We see here on the column on the left side, this is the ionosphere-free PCO values, which comes out using the L1, L2 pattern, and on the right side, the L1, L5 pattern. On the right side, we see then the difference between these two offsets, and we see that the difference is quite big. We see for the Javad antenna, the difference is roughly 1 centimeter. For the Leica antennas, which however is more or less 5 millimeter difference of the PCOs, depending which frequency you're actually using for the processing. Here is now just a small picture of the pattern itself. We see here on the left side, this is the PCV pattern of the L1, L2 combination. On the middle one, we see the pattern of a L1, L5 pattern. And on the right side, we see then actually the difference between these two, where we see here the scale goes up to plus minus 5 millimeters from the color range. Then again, I introduced this in the system translation biases. So I produced one solution using the L1, L2. These are the red dots. And I produced a solution using L1, L5 frequencies for the antennas. And I got the blue solutions. We see here clearly, especially for the up component, that we have quite a stable offset between time. This is also somehow to be expected as I introduce a different PCO offset. We also see that we have some difference in the north component. This is now for the station pods. Basically all 12 stations which I tested have a similar pattern, that this offset is quite stable over time. If I now actually go through all the stations and plot this mean offset for all stations, we see here on the right side the difference between these offsets using L1, L2 and the L1, L5 pattern. And we can say this is now the results for the FOC satellites. I have a similar behavior if I made the same table using the IOV satellites. However, I decided to show here the FOC as it's a bit more stable, as I have much more satellites which are contributing into this solution. And the main goal was to show it what is the impact of the L1, L5 pattern. We see here the difference between these inter-system translation biases in the up component, and we see that for the Javad, for these 4 Javad stations, especially the upper 3, they have in the mean difference is about 11 to 12 millimeters. And for the Leica antenna, we have a difference of roughly 8 millimeters between the solution using L1, L2 and the solution using L1, L5. If we compare then this solution to actually PCO differences, which we have between these two frequencies, we see that it's quite good matching. That we see here for the Javad, we have roughly 1 centimeter difference, and the estimation is more or less about 12 millimeters, I would say. So here we have kind of a common offset of roughly 2 to 3 millimeters. The same is valid for the Leica receivers, where you have a PCO of roughly 4 millimeter difference. And actually, the inter-system translation bias for the up component is 8 millimeters. So we see that some part of this translation could be explained by the PCO, and it fits quite well. Even though we still have roughly 4 millimeters for the like antenna, which actually is not coming from the PCO's difference itself. And this was then basically the test on the antenna side. And in conclusion, basically I can say I couldn't see, for the IOV pattern, I couldn't see an improvement or of a degradation of the solution. I could see that it improved the IOV translation biases, especially the repeatability over time. And for me, I would say it's kind of a recommendation to use the IOV patterns within the MGEX community. And for the test of this calibrated receiver antenna patterns of regarding L2, L5 frequency, basically, of course, it's kind of the outcome is that would be nice if we also have then the L5 patterns in the future for the IGS stations. As we can see, we have a clear impact on the station size if we use the L1 and L2 pattern instead of the actual pattern. And with this, I come to the end of my presentation.